Hi, welcome back. We're going to talk in this video about another test called the P-series test. Now you might be thinking, oh no, the P-series test, it's a new test. It's not. It is related to the integral test. The integral test is a very nice test. It works most of the time, but it's very lengthy, and as a result, we don't like to do the integral test that much. So we have is the P-series test. Now there are actually two tests that make the integral test a lot easier for us, so we can avoid it. One is the P-series test, and the other is what we call the comparison test, where we can compare. So in this video we're going to talk about the P-series. So what is a P-series? A P-series is in the form as the sum of n go to 1 to infinity, 1 over n to the p. Now be careful, it looks geometric, but it's not. So be very careful with that. You got to notice the difference between them. So where p is a positive constant. And for example, if we let p be 1, take a look here, 1 over 1 to the first, 1 over 1 to the second, 1 over 2 to the first, plus 1 over 3 to the first, and we would get like 1 plus 1/2 plus 1/3 plus, and it goes on forever. That's what these little dots mean right here. These little dots mean we're going to go on forever. Just like an English lesson, right? Now, if p is 1, we call this a harmonic series. Now, the integral test can be used to prove the P-series. Now, we're not going to go through a bunch of formal proofs for this. They take too long and not very exciting. But let's just take a look at one of these. Let's just take a look at the harmonic series. Now, if I want to take a look at the harmonic series, it's not geometric, it's not nth term, so I have to use the integral test. So I'm going to go and set that up. This becomes the limit as b goes to infinity from 1 to infinity 1 over x dx, which it becomes the limit as b goes to infinity of the natural log of x from 1 to b. Now we should be pretty good at this right now. If I let b go to infinity, if I plug it in, this is going to go to infinity. So therefore the integral diverges. And as a result, therefore my series will diverge by the integral test. Now that's not too hard to do, but remember, I shortcutted it. One, I didn't write the phrase f of x is positive, continuous, and decreasing. I didn't show my limits right, and I didn't write my answer in the correct form either. So this is definitely a very shortcutted version and would not be accepted on the AP exam. But what the P-series does is it makes it easier for us. Now, we're going to have some questions on this on your homework, but let's see what happens. Okay? Well, I know that if P was 1, this diverges. So I know that it will diverge for 1 over n. Now, if I tried 1 over n squared, you're going to find out that this will converge. So 1 over n squared. The same thing for 1 over n cubed. Now, if you did 1 over square root of n, you would find out that this would diverge. And you can test these out. If you did 1 over n times root n, well, that's just 1 over n to the 3/2. That would also converge. And so would 1 over n to the 4th. So if they converge, what do they all have in common? Now remember, this is a P-series. You're looking at the power. And if you guess that the power is greater than 1, they will converge. You're absolutely correct. They will diverge if P is between 0 and 1, inclusive. Right. And we don't normally include 0, though. I mean, it'd be kind of boring. Just be 1, 1, 1, 1, 1 plus 1 plus 1 plus 1. So if you let P be 0, it would just be 1 plus 1 plus 1 plus 1. Of course, that would diverge, okay? All right, so we don't really worry about that. Now, so for P-series, here we have it. 1 over n to the p. This is our rule. If p is greater than 1, our rule is that this will converge. We don't know what it will converge to, but we know it will. Remember, we're saying that the power is greater than 1. If we're between 0 and 1, we say that this will diverge. Again, we're saying that the power is between 0 and 1. And of course they did that, okay? The power there. There we go. And if we have a harmonic series, that's when we just proved, this will also diverge. So let's see. Let's take a look at a couple. So now, if I have 1 over n, the cubed root of n, well, this is not geometric. Remember, it's not geometric. It is not nth term. And integral test? Nope. Integral test is too long. It is, the integral test will work with this one, but it's just, I don't want to do it. So I look, if I were to rewrite this, n equals 1 to infinity, 1 over, this is n to the 1. There we go. I don't know what happened there. N to the 1/3. This is my p series. And you're going to write this. P, just like when we did geometric, p is equal to, we should say equal to 1/3, which is less than 1. Therefore, what would happen? This series will diverge. When we say the series diverges by p-series test. And there's our answer. Let's try the next one here. Ready? Over here, it's already written here. What can you say about p? Well, here p is 5 over 4, which is greater than 1. Therefore, we can say the series converges by p-series test. Alright, so I hope you enjoyed this video, and I'll see you guys later. Bye-bye.